Time feels simple, it moves forward, it is shared. It seems to tick the same way for everyone everywhere. A second passes, then another, and nothing about that rhythm feels uncertain. It is easy to believe that time is the quiet background of the universe, something so basic it does not need questioning. Clocks agree, days unfold, causes come before effects, everything appears orderly, but beneath that calm surface physics tells a stranger story. At the smallest scales ever measured, time behaves like a fixed reference, an invisible ruler against which change is compared. In that realm, events unfold according to a single shared ticking, assumed rather than examined. This assumption works so well that it quietly underpins much of modern technology. Yet when gravity enters the picture, that certainty dissolves. In the vast architecture of space-time, time no longer belongs to everyone equally. It stretches, it slows, it depends on motion, on mass, on where you are and how you move. There is no universal now, no master clock keeping the universe in step. Each path through space-time carries its own measure of duration, and somehow both descriptions are correct. Quantum mechanics relies on time as something absolute. General relativity insists that time is deeply relative. Both theories have been tested to extraordinary precision. Both describe reality with unsettling accuracy, and neither can simply be discarded. So the question is not whether time is strange. The question is how something can be both fixed and flexible, both shared and personal, both absolute and relative, without contradiction, and what that says about the universe you're quietly moving through right now. Welcome to the Sleepy Scientist. If you find this kind of calm, thoughtful exploration relaxing, consider liking the video and subscribing to the channel. And wherever time happens to be flowing for you right now, let us know where you're watching or listening from. Time feels like one of the simplest things in the world. It moves forward, it does not pause, it does not rewind, and it seems to treat everyone equally. A minute passes in much the same way whether it is spent waiting for a kettle to boil, walking down a familiar street, or lying awake in the dark. The seconds tick along, steady and reliable, as if they belong to the fabric of reality itself rather than to any particular place or person. This steadiness is so familiar that it rarely invites suspicion. Time feels like a shared background, something all events float within, rather than something that could behave differently from one moment or location to another. This sense of time as universal is deeply woven into everyday life. Clocks agree closely enough that disagreements are barely noticeable. Calendars line up across continents. Cause comes before effect. Breakfast happens before lunch, and night reliably follows day. From childhood onward, this regularity becomes part of how the world is understood. It feels less like an assumption and more like a fact. But this feeling is not the same thing as a physical law. Human experience of time is shaped first and foremost by biology. Inside the brain, time is not measured with anything resembling a clock. There is no ticking mechanism marking off equal intervals. Instead, the brain pieces together a sense of duration from changes, from movement, from memory, from anticipation, from sensory input. When very little changes, time can feel slow. When a great deal happens at once, hours can seem to vanish. Neuroscientific research has shown that the brain operates using temporal integration windows. These are short spans, often lasting fractions of a second, during which sensory information is gathered and blended into a single perceptual moment. David Eagleman and other researchers studying time perception have demonstrated that what feels like a smooth flow of time is actually a constructed sequence of overlapping snapshots. The brain stitches these together so seamlessly that the construction process itself disappears from awareness. This is why time can stretch during moments of fear or novelty. When something unexpected happens, the brain records more detail. More information means more internal change, and more change creates the impression of a longer duration. By contrast, familiar routines compress subjective time. When days look the same, fewer distinct memories are formed, and looking back, the time seems to have passed quickly. This subjective elasticity can be measured. Experiments comparing perceived duration with objective clock time consistently show that emotion, attention, and novelty can alter experienced time by large factors. In some situations, people report intervals feeling several times longer or shorter than they actually are. Yet despite this variability, the brain still produces a strong overall sense that time itself is stable. The variability is interpreted as a quirk of experience, not as a property of time. Biological rhythms reinforce this illusion of regularity. Circadian rhythms driven by biochemical feedback loops and regulated by light exposure create a roughly 24-hour cycle that anchors sleep, wakefulness, and hormonal activity. Heartbeats, breathing patterns, and neural oscillations provide additional internal pacing. These rhythms evolved because they are useful. They allow prediction, they allow coordination, they allow survival. From an evolutionary perspective, treating time as steady and shared is an advantage. If time were perceived as inconsistent or unreliable, planning would become difficult. Coordinated action would break down. The brain therefore evolved to assume regularity wherever possible. This assumption works extraordinarily well at human scales. Philosophers noticed the difference between lived time and measured time long before modern neuroscience. Henry Bergson described what he called duration, a flowing, qualitative experience of time that could not be captured by clocks or equations. He argued that scientific time, broken into equal units, missed something essential about how time is actually lived. While later physics did not adopt Bergson's conclusions, the distinction he drew remains important. There is the time that is experienced and the time that is measured. Modern science strongly supports this separation. Psychological time is constructed. Physical time, whatever it turns out to be, does not depend on attention, emotion, or memory. The two interact, but they are not the same thing. This distinction matters because intuition is shaped almost entirely by psychological time. The feeling that time is universal comes from shared biological rhythms and shared environments, not from direct access to the structure of reality. Humans live at similar speeds, under similar gravitational conditions, moving relatively slowly compared to cosmic limits. Under these conditions, time behaves in ways that closely match intuition. But intuition is always local. It reflects the scale at which a species evolved. Ants experience time differently from humans. Birds process visual information faster than humans do, effectively experiencing more moments per second. Even within a single lifetime, time perception changes. Childhood years feel long, while later decades seem to accelerate. None of this reflects changes in physical time itself. It reflects changes in brains. At this point, it becomes possible to introduce a quiet challenge to everyday certainty. Julian Barber, a physicist known for questioning deeply held assumptions, has argued that time may not be a fundamental ingredient of the universe at all. In some of his work, time is treated not as a flowing entity, but as an emergent ordering of change. According to this view, what is experienced as time passing may arise from relationships between physical configurations, not from an underlying temporal river carrying everything along. Whether or not this idea ultimately proves correct, its importance lies in what it reveals about intuition. If time itself can be questioned at a fundamental level by serious physics, then everyday certainty about its nature cannot be taken as evidence. This does not mean intuition is wrong. It means intuition is specialized. The feeling that time is shared and uniform is accurate within a narrow domain. At human speeds, over human distances, under Earth's gravity, time behaves in a way that is so close to universal that differences are negligible. Atomic clocks placed a few meters apart tick at almost the same rate. The effects that would challenge intuition exist, but they are extremely small under ordinary conditions. To put this in perspective, time dilation effects predicted by modern physics at walking speed differ from everyday clock time by amounts far smaller than a billionth of a second over an entire lifetime. No biological system could detect this. No perception could register it. From the brain's point of view, time really is universal. But scale matters. When speeds increase toward the speed of light, or when gravity becomes intense, those tiny differences grow. What was once negligible becomes measurable. What was once safely ignored becomes central. The assumptions that served biology so well begin to fail physics. This is a recurring theme in science. Intuition works best where it evolved. It struggles outside that range. Just as the Earth feels flat when standing on its surface, time feels uniform when living slowly on a planet with modest gravity. In both cases, the feeling is understandable, useful, and incomplete. The key point is not that human experience is misleading, but that it is limited. Psychological time is an internal model, optimized for coordination and survival, not for revealing the deeper structure of the universe. It smooths over variation. It averages out difference. It hides complexity unless that complexity becomes unavoidable. This is why time feels like a background rather than a participant, why it feels the same in every place, why it seems to flow independently of matter and motion. These impressions are not arbitrary. They are the natural outcome of biology, operating within a narrow physical regime. Once that regime is left behind, certainty begins to loosen. The calm, steady time of everyday life turns out to be a special case, not a universal rule. Understanding why it feels so convincing is the first step toward understanding why physics eventually had to let it go. For most of human history, time was not treated as a mystery. It was treated as a certainty. Long before laboratories, equations, or precision clocks, time appeared to move with reassuring regularity. The sun rose and set. Seasons returned. Shadows lengthened and shortened in predictable ways. These repeating patterns made it natural to think of time as something external to the world, something that existed independently and flowed on its own, carrying events along with it. This intuition found its most influential scientific expression in the work of Isaac Newton. In the late 17th century, Newton described time as absolute, true, and mathematical. In his view, time flowed uniformly everywhere, without reference to anything external. It did not depend on motion. It did not depend on matter. It did not depend on observers. Time existed in the same way space existed, as a vast invisible stage on which the universe unfolded. This idea fit perfectly with Newton's mechanics. Motion could be described as change in position over time. Forces produced acceleration over time. Causes preceded effects in a clean, orderly sequence. Every clock, no matter where it was placed or how it moved, was assumed to be measuring the same underlying temporal flow. The success of this framework was extraordinary. Using Newtonian mechanics, scientists could predict the motion of planets with remarkable accuracy. They could calculate trajectories, tides, and eclipses. The same equations worked whether an object was dropped from a tower or launched across a field. Time functioned as a shared reference that made the entire system coherent. In this framework, time did not need explanation. It was assumed. But not everyone agreed that this assumption was inevitable. Gottfried Wilhelm Leibniz, a contemporary of Newton and an equally formidable thinker, argued that time should not be treated as an independent entity at all. Instead, he proposed a relational view. According to Leibniz, time was nothing over and above the ordering of events. There was no empty time flowing in the background. There were only changes, and time was a way of describing the relationships between those changes. If nothing happened, Leibniz argued, there would be no time to speak of. Time was not a container. It was a measure of sequence. This disagreement between Newton and Leibniz was not merely personal or philosophical. It revealed a deep divide about what time actually is. On one side was the substantival view. In this picture, time exists in its own right, much like a substance. Events happen in time, but time itself does not depend on those events. It is there whether anything occurs or not. On the other side was the relational view. Here, time has no independent existence. It emerges from the relationships between physical processes. Without change, there is no time. For centuries this debate remained unresolved, but it mattered less than one might expect because Newton's version worked so well. Classical mechanics quietly took substantival time as its foundation. Equations were written with time as an independent variable. Motion was described as position changing smoothly with respect to time. Forces acted continuously over time. None of this required time to be questioned. Time simply sat there, steady and unquestioned, doing its job. This is what is meant by time as a silent background parameter. In classical physics, time is not something that interacts with matter. It does not bend, stretch, or respond. It does not need equations of its own. It is assumed to tick uniformly everywhere, providing a shared reference against which all motion can be compared. This assumption simplified everything. Because time was universal, clocks could be synchronized without ambiguity. Because it flowed at the same rate everywhere, calculations performed in one place applied equally well elsewhere. Because it was independent of motion, the same equations described slow-moving carts and fast-moving planets. The practical benefits of this assumption cannot be overstated. It allowed physics to become predictive, precise, and widely applicable. It turned nature into something that could be described with clean mathematical relationships. And because the predictions worked, the assumptions faded into the background. This background role shaped how later theories were built. When new physical ideas emerged in the 19th and early 20th centuries, they inherited this picture almost by default. Time was already there. It already worked. There was no pressing reason to question it. This is especially important for understanding how time entered later theories of the microscopic world. When physicists began exploring atoms, radiation, and energy at very small scales, they carried classical time with them. Experiments were timed. Processes unfolded in sequence. Measurements occurred at specific moments. Time remained the independent parameter that ordered change. The equations describing early atomic phenomena were written with time as a given. It was assumed to be shared by all observers. It was assumed to flow uniformly. It was assumed to be the same kind of time Newton had described centuries earlier. This inheritance was not careless. It was practical. At the scales being explored, the assumptions of classical time worked extremely well. Atomic processes unfolded over intervals measured in fractions of a second or less. Even the fastest particles moved at speeds far below cosmic limits. Gravitational effects were negligible. Under these conditions, time behaved exactly as expected. There was no experimental hint that time might behave differently. This meant that the philosophical divide between substantival and relational time remained largely academic. Physics could proceed without choosing sides. Time could be treated as absolute in practice, even if its deeper nature remained unsettled. But the choice to treat time as a background parameter had consequences. Once time is placed outside the system, it cannot be affected by the system. Once it is assumed to be universal, it cannot vary from place to place. Once it is taken as independent, it cannot be influenced by motion or matter. These assumptions became deeply embedded. They shaped how equations were written. They shaped how experiments were designed. They shaped what kinds of questions seemed reasonable to ask. Time was not something to be explained. It was something used to explain everything else. This is why the eventual challenges to classical time were so disruptive. They did not merely add new effects, they questioned the foundation itself. But from the perspective of classical mechanics, there was no reason to anticipate this. Time behaved exactly as expected within the domain where classical physics applied. The universe, at everyday speeds and distances, appeared to run on a single shared clock. The quiet strength of Newton's time was that it worked everywhere people could test it. Only much later, when physics pushed beyond familiar scales, would the limits of this assumption become visible. And when those limits appeared, they did not gently modify the old picture. They forced a complete rethinking of what time could be. For now, what matters is how firmly the classical view took hold. Time as an absolute universal backdrop became the default setting for physics. It shaped centuries of thought. It framed how motion, causality, and change were understood, and it was so effective that it became almost invisible. This invisibility is precisely why its eventual unraveling would be so surprising. The stage had been set long before anyone realized it. At the turn of the 20th century, physics began to encounter problems that classical ideas could not smooth over. Certain observations simply refused to fit. Hot objects glowed with patterns classical theory could not predict. Electrons behaved in ways that defied familiar motion. Light, once thought to be a continuous wave, sometimes acted like a stream of discrete packets. These were not small discrepancies. They were cracks running through the foundations. The first decisive step came from Max Planck. In 1900, while studying the spectrum of radiation emitted by heated objects, Planck found that the data could only be explained if energy were exchanged in discrete amounts. He introduced the idea that energy comes in tiny packets, later called quanta. This move was cautious, almost reluctant, but it worked. A problem that had resisted explanation suddenly fell into place. What Planck did not do was question time. In his calculations, energy changed over time in exactly the way classical physics expected. Time remained a smooth, continuous parameter, flowing uniformly in the background. The novelty lay in how energy behaved, not in when it changed. As the quantum revolution gathered momentum, this pattern repeated. Niels Bohr proposed a model of the atom in which electrons occupied discrete orbits and emitted or absorbed energy only when jumping between them. These jumps were abrupt, but they were still described as happening at particular moments. Time ordered the sequence of events without complication. An electron was in one state, then later in another. Werner Heisenberg pushed further, abandoning visual pictures of orbits altogether. Instead, he focused on observable quantities such as transition frequencies and intensities. His formulation of quantum mechanics replaced classical trajectories with arrays of numbers that encoded how systems changed. Yet even here, time remained untouched. Observables changed as time passed. The passage itself was taken for granted. Erwin Schrödinger provided the most famous equation of the new theory, describing how a quantum state evolves. This equation treats time as an external parameter that labels change. Given a state at one moment, the equation specifies how it develops at later moments. Time does not fluctuate. It does not interact. It simply marks progression. Across these early formulations, a consistent pattern emerges. Quantum mechanics radically altered how matter and energy were described, but it left time almost exactly where classical physics had placed it. This was not an oversight. It was a deliberate choice driven by necessity. The phenomena being studied occurred at extremely small scales, but over times that were still long compared to fundamental limits. Atomic transitions unfolded over tiny fractions of a second, but they could still be ordered cleanly. Experiments involved preparation, evolution, and measurement, all occurring in a definite sequence. Treating time as an external parameter allowed physicists to focus on the genuinely new features without destabilizing everything at once. Paul Dirac played a crucial role in shaping this formal structure. Dirac sought a unified, elegant framework for quantum mechanics, one that could encompass the different approaches developed by Heisenberg and Schrödinger. In doing so, he made explicit what had been implicit all along. Time was not an observable within the theory. It was a parameter that indexed change. Operators represented measurable quantities like position and momentum, but time sat outside this algebra, unaffected by quantum uncertainty. This formal separation was powerful. It allowed quantum mechanics to be expressed with remarkable clarity and predictive accuracy. But it also introduced an asymmetry that some physicists found unsettling. In classical mechanics, time and position are treated differently, but the distinction rarely causes trouble. In quantum mechanics, where observables are associated with operators and uncertainties arise naturally, the absence of a time operator stands out. Wolfgang Pauli articulated this concern sharply. Pauli pointed out that if time were treated as an observable in the same way as position, it would lead to contradictions within the theory. Specifically, a self-consistent time operator would imply unphysical energy spectra. To avoid this, time had to remain external. It could not be placed on equal footing with other quantities. This observation is now known as Pauli's objection. It was not a minor technical detail. It revealed that quantum mechanics as formulated could not easily accommodate time as something measurable within the system. Time was required for the theory to function, but the theory itself could not describe time in the same way it described everything else. This created a quiet tension. On one hand, the theory worked extraordinarily well. Quantum mechanics predicted atomic spectra with astonishing precision. It explained chemical bonding, electrical conduction, and the behavior of light and matter with unmatched success. There was no experimental reason to doubt its foundations. On the other hand, some of its architects were uneasy. They knew that time was being treated differently, not because the universe demanded it, but because the mathematics did. The choice was pragmatic rather than principled. Time was kept classical so that everything else could become quantum. This discomfort rarely surfaced in popular accounts, but it was present in the background. Quantum mechanics, for all its radical departures, relied on a familiar scaffold. It borrowed time from the classical world and built something new upon it. The reason this borrowing seemed safe lies in scale. Quantum systems studied in laboratories were small and fast, but not fast enough for relativistic effects to matter. Their motions were slow compared to the speed of light. Gravitational influences were negligible. Under these conditions, classical time was an excellent approximation. It behaved as a shared, universal parameter to extraordinary accuracy. To appreciate how accurate, consider that relativistic time differences at everyday laboratory speeds amount to changes far smaller than a trillionth of a second over the duration of typical experiments. Such differences are not merely difficult to detect, they are irrelevant for practical purposes. So quantum mechanics proceeded with confidence. Time was treated as something that flowed identically for all systems involved. Preparation happened at one time, evolution occurred over an interval. Measurement took place later. This structure mirrored classical experiments and fit seamlessly into existing experimental practice. But the cost of this convenience was conceptual completeness. Quantum mechanics never explained what time is. It never described how time might be affected by quantum processes. It never allowed time itself to fluctuate, entangle, or become uncertain. Time remained outside the quantum world, even as that world expanded to include almost everything else. Some founders suspected this could not be the final word. They understood that a theory in which matter and energy are quantized, but time is not, might eventually run into limits. They did not yet know where those limits lay, but the asymmetry was impossible to ignore forever. At the same time, there was no clear alternative. Any attempt to treat time as an observable ran into Pauli's objection. Any attempt to quantize time threatened the consistency of the theory. The safest option was to proceed with what worked and leave deeper questions for later. This decision shaped decades of physics. Quantum mechanics became the foundation of modern technology. Lasers, transistors, magnetic resonance imaging, and atomic clocks all rely on its principles. In every case, time appears as an external parameter, measured by classical devices and fed into quantum equations. The theory's success reinforced its assumptions. If something works perfectly, there is little incentive to question its structure. Yet beneath this success, a subtle mismatch was taking shape. Quantum mechanics assumed a single, shared time for all systems. That assumption would later come into contact with a theory in which time behaves very differently. And when that contact occurred, the quiet choices made at the birth of quantum mechanics would suddenly matter a great deal. For now, what is important is not that quantum mechanics got time wrong. It is that quantum mechanics chose not to talk about time at all. Time was placed outside the system, treated as given, and used as a tool rather than a subject of study. This choice made the theory possible. It also ensured that time would remain an unresolved question at the heart of modern physics. The seeds of that question were planted from the very beginning, hidden beneath equations that work too well to disturb. Quantum mechanics treats time in a very particular way. It assumes that time is already there, not emerging, not fluctuating, not interacting, but quietly present in the background, flowing smoothly and uniformly, the same everywhere for every system involved. This assumption is so deeply embedded that it can be easy to miss, especially because quantum mechanics is otherwise so radical. To understand why this choice was made, it helps to introduce a key idea: background dependence. A background-dependent theory is one that relies on a fixed structure that does not respond to the physical processes happening within it. In classical mechanics, space and time form such a background. Objects move through space as time passes, but space and time themselves do not change in response. They are passive stages, not active participants. Non-relativistic quantum mechanics inherits this structure almost unchanged. The quantum state of a system evolves over time, but time itself is not part of the system being described. It does not bend, stretch, fluctuate, or become uncertain. It provides a stable reference against which change is measured, much like a perfectly reliable stopwatch that never interacts with what it is timing. This means that quantum mechanics borrows its time parameter directly from classical physics. The time that appears in quantum equations is the same time that orders classical events. It is assumed to be universal, external, and absolute. Every quantum system in an experiment is taken to evolve with respect to the same shared clock, regardless of where it is or how it moves. This borrowing was not accidental. Quantum mechanics was developed to explain phenomena that classical physics could not, but it was not developed in isolation. Early quantum experiments were conducted in laboratories built according to classical assumptions. Measurements were timed with classical clocks. Signals travelled at speeds slow enough that relativistic effects could be ignored. Gravitational influences were negligible. Within this domain, classical time worked perfectly. At the scale of atoms and molecules, time differences caused by motion or gravity are extraordinarily small. For a particle moving at speeds typical of laboratory experiments, relativistic time dilation amounts to changes so tiny they would take many millions of years to accumulate into a measurable second. For all practical purposes, time really does behave as a shared, absolute parameter. This made it natural to keep time classical while quantizing everything else. In standard quantum theory, quantities like position, momentum, and energy are associated with operators. These operators do not generally commute, which leads to uncertainty relations and fundamentally probabilistic outcomes. Time, however, is not treated this way. It is not represented by an operator. It does not have uncertainty in the same sense. Time is not quantized. There is no smallest unit of time in standard quantum mechanics. Time is treated as continuous, capable of being divided without limit, just as it was in classical mechanics. Quantum theory introduces discreteness in energy levels and other quantities, but not in time itself. This asymmetry is striking. Energy comes in discrete levels in bound systems. Angular momentum is quantized. Even fields can be described in terms of discrete excitations. Yet time remains smooth and unbroken, flowing evenly beneath it all. The reason for this is not that time has been shown to be continuous at all scales. It is that the theory requires it to be continuous in order to function as formulated. If time were treated as an observable subject to quantum uncertainty, the standard structure of quantum mechanics would break down. Evolution would become ill-defined. Predictions would lose their coherence. The clean separation between preparation, evolution, and measurement would blur. By keeping time external and absolute, quantum mechanics preserves a clear notion of sequence. One can say what happens first, what happens later, and how long processes last. This clarity is essential for making predictions and comparing them with experiments. It is also deeply convenient. Laboratory practice depends on synchronized clocks. Experiments are run for specific durations. Measurements are triggered at specific times. Data is recorded in time-stamped sequences. Treating time as universal allows all of this to proceed without ambiguity. In this sense, absolute time is not a metaphysical commitment. It is a practical tool. The equations of quantum mechanics are designed to tell how a system changes as time passes. They do not attempt to explain what time is or where it comes from. Time is assumed, not derived. This assumption is so effective that it fades into the background. Quantum mechanics becomes a theory of states evolving in time, rather than a theory of time itself. However, some physicists have pointed out that this choice comes with a conceptual cost. Carlo Rovelli, among others, has emphasized that treating time as an external background is incompatible with the way gravity is described in general relativity. In that theory, time is not fixed. It is part of the dynamical structure of space-time. It responds to mass and energy. It behaves differently in different regions. From this perspective, the absolute time used in quantum mechanics looks suspiciously classical. Rovelli has argued that this background-dependent treatment of time is not a fundamental feature of nature, but a sign that quantum mechanics is incomplete as a description of reality at all scales. According to this view, quantum theory works beautifully within a fixed background, but it cannot be the final word if the background itself is subject to change. This critique does not diminish the success of quantum mechanics. It clarifies its domain of validity. Quantum mechanics excels when the geometry of space and time can be treated as fixed. It struggles when that geometry becomes dynamical. The problem is not with quantization, but with the assumption that there is a single universal clock ticking in the background. The reason this assumption has been so successful is that gravity is weak in most everyday situations. On Earth, gravitational time dilation between the floor and the ceiling of a room is measurable only with extremely precise atomic clocks, and even then the difference amounts to tiny fractions of a second over many years. In a laboratory setting, these effects are negligible. Time behaves as if it were absolute. Because of this, quantum mechanics can safely ignore gravity and still produce extraordinarily accurate results. But this safety is conditional. Absolute time simplifies predictions because it removes the need to account for differences between observers. Everyone agrees on what time it is. Everyone agrees on how long processes last. This shared framework allows equations to be written cleanly and solutions to be compared directly with experiments. It also allows quantum theory to be taught, learned, and applied without constantly revisiting foundational questions. Time is simply there, doing its job quietly and reliably. The price of this simplicity is that time becomes conceptually detached from the physical systems it orders. Quantum mechanics tells how particles behave, how fields fluctuate, how probabilities evolve. It does not tell how time itself behaves. Time is assumed to be immune to quantum effects. It does not become entangled. It does not decohere. It does not fluctuate. This is not because such effects have been ruled out experimentally. It is because the theory does not include the tools to describe them. In effect, quantum mechanics draws a line. Everything on one side of the line is subject to quantum rules. Everything on the other side is classical. Time sits firmly on the classical side. This division is remarkably stable within its intended domain. As long as gravitational effect can be ignored and relativistic speeds are not involved, treating time as absolute produces predictions that match experiments to astonishing precision. This is why the theory has been trusted for so long without revision. But stability is not the same as universality. The moment one attempts to apply quantum principles to systems where gravity matters, such as near extremely massive objects, or at the earliest moments of the universe, the assumption of absolute time becomes problematic. There is no single clock that all observers can agree on. There is no fixed background to borrow. This is where the conceptual clash begins to emerge. Quantum mechanics assumes a universal time parameter. Gravity refuses to provide one. The two frameworks describe reality in fundamentally different ways, and the difference is not superficial. For now, it is enough to recognize why quantum mechanics treats time as absolute. It does so because it was built within a classical background. It does so because that choice works. It does so because abandoning it would require rethinking the theory from the ground up. Time, in quantum mechanics, is not absolute because nature demands it. It is absolute because the theory needs it to be. That distinction matters. Quantum mechanics did not earn its reputation through philosophy. It earned it through experiments. Again and again, predictions derived from quantum theory have been tested against reality with extraordinary precision, and again, reality has agreed. In laboratories around the world, tiny systems behave exactly as the equations say they should, provided one quiet assumption holds steady in the background. That assumption is shared time. Every successful quantum experiment relies on synchronized clocks. Preparation happens at a known moment. A system evolves for a known duration. A measurement is made at a later moment. The results are compared against predictions that depend explicitly on how much time has passed between these stages. Without agreement about timing, the theory could not be tested at all. This reliance is so routine that it often goes unnoticed. Consider a simple atomic experiment. An atom is prepared in a specific state. It is then allowed to evolve under controlled conditions. After a carefully measured interval, it is probed to see how its state has changed. The probability of different outcomes depends directly on the length of that interval. If two laboratories disagreed about time, they would disagree about results. They do not. This agreement is not accidental. It is enforced by some of the most precise instruments ever built. Atomic clocks sit at the heart of modern timekeeping. These devices measure time by tracking the frequency of radiation absorbed or emitted when electrons in atoms transition between energy levels. Because these transitions are governed by quantum mechanics, they are extraordinarily stable. The oscillations involved occur hundreds of trillions of times per second, providing a natural rhythm far more reliable than any mechanical process. Modern atomic clocks are so precise that they would lose or gain less than a second over the age of the universe, measured in billions of years. At this level of precision, even tiny effects become visible. Changes in altitude of a few tens of centimeters can be detected through shifts in clock rates caused by gravity. The development and refinement of these clocks has been driven by the field of quantum metrology, which uses quantum systems to make ultra-precise measurements of physical quantities. Time is the most refined of these quantities because it underpins all others. Length, frequency, and even electrical standards are defined in terms of time. Institutions like the National Institute of Standards and Technology have played a central role in this work. By building and comparing atomic clocks of increasing precision, researchers have not only improved technology, but also tested the foundations of physics itself. Quantum mechanics continues to pass these tests with remarkable consistency. The success of atomic clocks demonstrates something subtle but important. Quantum systems evolve in time exactly as predicted, provided that time is treated as a shared classical parameter. The theory assumes that every part of the experiment agrees on what time it is, and in practice this assumption holds to astonishing accuracy. This shared timing extends beyond clocks sitting quietly on laboratory benches. Some of the most striking demonstrations come from experiments designed to test the deepest features of quantum theory, including entanglement. In these experiments, particles are prepared in correlated states and then sent to distant locations. Measurements are made independently, and the correlations between outcomes are compared. Alain Aspect's experiments in the early 1980s were among the first to convincingly demonstrate quantum entanglement in a way that ruled out classical explanations. In these tests, pairs of photons were generated together and then separated. Measurements were performed at different locations, with the settings chosen rapidly and independently. Timing was crucial. The measurements had to be coordinated with exquisite precision to ensure that no signal travelling at or below the speed of light could influence both outcomes. This required synchronized clocks and carefully controlled delays. The correlations observed matched quantum predictions exactly. Once again, time behaved as expected. The photons did not care which laboratory they were measured in. The correlations depended on relative timing, but that timing could be agreed upon. The experiment worked because everyone involved shared the same temporal framework. Similar requirements appear in modern quantum technologies. Quantum communication systems rely on synchronized timing to encode and decode information. Quantum computing experiments depend on precisely timed sequences of operations, often lasting only millionths or billionths of a second. Errors in timing translate directly into errors in results. Across all of these domains, quantum mechanics performs flawlessly within its intended framework. This success can be tempting. When a theory works this well, it feels complete. But experimental success does not automatically resolve conceptual questions. Quantum mechanics tells us how systems evolve with time. It does not tell us what time is. The theory assumes a background clock and uses it effectively, but it does not explain why such a clock exists or how it behaves under all conditions. The very instruments used to test quantum theory quietly reinforce this assumption. Atomic clocks are quantum systems, but they are treated as external references rather than as objects whose own timekeeping might fluctuate in a fundamentally quantum way. They are designed to suppress noise, decoherence, and uncertainty, producing a stable classical signal. In other words, quantum systems are used to build clocks that behave classically. This arrangement works beautifully. It also hides deeper questions. The extraordinary agreement between quantum predictions and experiments occurs in regimes where gravity is weak and relative motion is slow. Under these conditions, time behaves as if it were absolute. Differences between observers are so small that they can be ignored without consequence. Even when those differences become measurable, as in comparisons between clocks at different altitudes, they are treated as corrections applied to an underlying shared framework. The clocks are adjusted. The agreement is restored. From the perspective of quantum mechanics, this is not a problem. It is a feature. The theory delivers predictions that match observation to many decimal places. There is no experimental crisis demanding revision. Yet from a broader perspective, something interesting is happening. The more precisely time is measured, the more it becomes clear that it is not perfectly uniform in all circumstances. Atomic clocks reveal tiny variations caused by gravity and motion. These variations are not predicted by quantum mechanics itself. They are accounted for by another framework entirely. Quantum experiments succeed because they operate within a domain where these effects can be treated as external adjustments rather than internal dynamics. This is why the success of quantum timekeeping does not settle the deeper issue. It demonstrates that treating time as absolute is an extraordinarily good approximation under laboratory conditions. It does not demonstrate that time is fundamentally absolute. There is a quiet distinction here between reliability and completeness. Quantum mechanics is reliable. Its predictions are among the most accurate ever produced by science. But the theory does not attempt to describe situations in which the background structure of time itself becomes dynamic. It assumes that such situations lie outside its scope. As experimental precision increases, the boundary between these domains becomes more visible. Clocks now measure effects that were once purely theoretical. Differences in gravitational potential that would have been irrelevant a century ago are now part of routine calibration. These observations point toward a picture in which time behaves differently depending on context. Quantum mechanics accommodates this by working within a fixed background and allowing corrections from elsewhere. It does not attempt to generate the background itself. The success of this strategy has been overwhelming. Modern navigation systems rely on atomic clocks corrected for relativistic effects. Telecommunications depend on synchronized timing across continents. Scientific experiments coordinate events separated by vast distances with sub-nanosecond accuracy. All of this works because quantum mechanics and classical timekeeping cooperate seamlessly. But cooperation is not unification. The fact that quantum mechanics needs time to be classical in order to function smoothly suggests that time occupies a special status in the theory. It is both essential and unexplained. It is everywhere and nowhere within the formalism. This tension does not undermine the achievements of quantum physics. It highlights their context. Quantum mechanics has been tested in regimes where time behaves in a way that matches classical expectations. In those regimes, it performs with stunning success. Outside them, the theory remains silent. As experimental techniques continue to advance, physics is gradually being pushed towards situations where these assumptions can no longer be taken for granted. When that happens, the question will not be whether quantum mechanics worked in the past. It will be whether its quiet treatment of time can survive contact with the universe in which time itself is not fixed. By the end of the 19th century, classical physics was showing signs of strain, not in its ability to describe everyday motion, which it still did extremely well, but in its attempt to account for light and electromagnetism. Experiments involving electricity, magnetism, and radiation were producing results that did not sit comfortably within Newton's framework. The equations worked, but their interpretation was becoming increasingly uneasy. At the center of this tension was light. According to classical ideas, waves required a medium. Sound needed air. Water waves needed water. By analogy, light was assumed to propagate through a medium as well, an invisible substance called the luminiferous ether. This ether was imagined as filling all of space, providing a universal reference frame against which motion could be measured. But careful experiments failed to detect it. Measurements designed to reveal Earth's motion through the ether produced no effect. Light appeared to travel at the same speed regardless of the motion of the source or the observer. This was deeply puzzling. In Newtonian physics, speeds add. If you move toward a light beam, you should measure it moving faster. Yet light refused to cooperate. The mathematics of electromagnetism, developed earlier in the century, made the problem even sharper. James Clerk Maxwell's equations predicted that electromagnetic waves travel at a specific speed determined by electrical and magnetic constants. That speed appeared to be built into the structure of the equations themselves. It was not relative to anything else. This is where Albert Einstein enters the story. Einstein was not initially trying to overturn concepts of time. He was trying to make sense of physics. In particular, he wanted the laws of nature to look the same to all observers who were moving at constant speeds relative to one another. This principle, known as the principle of relativity, had already worked beautifully in mechanics. Einstein extended it to electromagnetism. The challenge was clear. If the speed of light was fixed by the laws of electromagnetism, and if those laws were to be the same for all observers, then something had to give. Either the principle of relativity would fail, or classical ideas about space and time would. Einstein chose space and time. This choice was not philosophical, it was forced by consistency. Others had come close before him. Hendrik Lorentz had developed mathematical transformations that explained why experiments failed to detect motion through the ether. These transformations showed how lengths and time intervals would have to change for moving observers in order to preserve the form of Maxwell's equations. In Lorentz's work, moving clocks slowed down and moving objects contracted, but these effects were often treated as physical distortions caused by motion through the ether. Einstein took a different step. He removed the ether entirely. Instead of treating Lorentz's transformations as corrections applied to objects moving through a hidden medium, Einstein treated them as statements about space and time themselves. There was no preferred frame, no absolute background. The transformations were not disguising motion relative to an unseen substance. They were revealing how measurements of space and time depend on the state of motion of the observer. This shift had immediate consequences. If all observers measure the same speed of light, then they cannot all agree on time. Events that appear simultaneous to one observer will not appear simultaneous to another if they are in relative motion. This is not a matter of perception or delay. It is a fundamental feature of how time is structured. Henri Poincaré had already hinted at this idea by emphasizing the operational definition of simultaneity. He argued that time should be defined by procedures involving clocks and signals, not by metaphysical assumptions. To decide whether two distant events happen at the same time, one must specify how clocks are synchronized and how information travels between them. Einstein took this operational view seriously. He defined simultaneity using light signals. Two clocks are synchronized if light sent from one reaches the other and returns in a symmetric way, assuming the speed of light is the same in both directions. This definition works beautifully, but it has an important implication. Observers in relative motion using the same procedure will not agree on which distant events are simultaneous. There is no universal now. This realization marked the end of time as an absolute quantity. In Newtonian physics, time flows uniformly everywhere, independent of motion. In Einstein's framework, time becomes intertwined with motion itself. How fast a clock ticks depends on how it moves. How events are ordered in time depends on the observer's state of motion. This was not an optional feature. It was required to preserve the consistency of physical laws. If time had remained universal, the equations of electromagnetism would have contradicted the principle of relativity. If the principle of relativity had been abandoned, vast swathes of experimental evidence would have become inexplicable. The only viable path forward was to let go of absolute time. Einstein's theory of special relativity did exactly that. Clocks moving relative to one another tick at different rates. This effect, known as time dilation, is not an illusion. It has been measured directly. Particles created in Earth's atmosphere live longer when moving at high speeds. Atomic clocks flown on aircraft accumulate measurable differences compared to those left on the ground. These effects are small at everyday speeds. A person walking down the street will not notice their watch slowing, but the effects grow with speed, becoming significant as velocities approach the speed of light. The key point is not the size of the effect, it is its inevitability. Time lost its universal status because physics demanded it. The structure of the laws required time to behave differently for different observers. There was no way to preserve consistency without allowing this. This is why relativity should not be understood as a philosophical stance about reality. It is a practical response to experimental facts. It resolves contradictions between well-tested theories. It unifies mechanics and electromagnetism under a single framework. Einstein did not set out to make time strange. He set out to make physics work, Once time is allowed to vary between observers, space can no longer remain separate. Measurements of distance also depend on motion. Lengths contract along the direction of motion. Space and time become entangled in a precise mathematical way. This leads naturally to a new picture. Instead of thinking of space as a three-dimensional stage and time as a separate flowing entity, it becomes more accurate to think in terms of a unified structure. Events are located not just in space or in time, but in space-time, a combined framework where the two are inseparable. In this picture, time is not something that exists independently. It is one aspect of how events are related. Different observers carve this structure up differently, separating it into space and time according to their motion. This does not mean that anything goes. There are strict rules governing how these separations work. The laws are precise, testable, and deeply constrained. Relativity replaces absolute time with relational time, but it does so in a disciplined way. The calm strangeness of this result is easy to underestimate. Every observer carries their own clock. Every clock measures its own proper time. There is no master clock ticking behind the scenes. Yet all observers agree on the laws governing how their clocks relate to one another. This balance between flexibility and order is one of the defining achievements of modern physics. What matters here is not the mathematical machinery, but the conceptual shift. Time stopped being a silent background. It became something that depends on motion, something that responds to physical conditions, something that must be defined operationally rather than assumed. This rethinking of time did not arise from abstract speculation. It arose because nature refused to behave in any other way. And once time was allowed to change, the door opened to an even deeper transformation. Once time is no longer universal, its behavior becomes something that can be examined, tested, and measured. Special relativity does exactly this. It does not treat time as a vague idea or a philosophical curiosity. It treats time as a quantity that depends on motion, governed by precise rules that can be checked against experiment. One of the most famous consequences of this is time dilation. Time dilation means that a clock in motion relative to an observer will tick more slowly than a clock at rest with respect to that observer. This is not a mechanical failure. The clock is not broken. It is doing exactly what the laws of physics require it to do. To understand why, it helps to focus on how time is measured. A clock measures time by counting regular physical processes. These processes might involve vibrations of atoms, oscillations of electromagnetic fields, or decays of particles. In special relativity, all such processes are affected by motion in the same way. When an object moves, the path it takes through space-time changes. The amount of time accumulated along that path, known as proper time, depends on the object's speed. Faster motion through space corresponds to slower accumulation of proper time. This effect is tiny at everyday speeds. If a person walks across a room, the difference between their time and the time of someone standing still is so small that it would take many millions of years to add up to a noticeable fraction of a second. But as speed increases, the effect grows. At speeds approaching the speed of light, the difference becomes dramatic. This is not a theoretical curiosity. It has been observed repeatedly. Particles called muons are created high in Earth's atmosphere when cosmic rays strike air molecules. Muons have very short lifetimes when at rest, lasting only a few millionths of a second. At first glance, they should decay long before reaching the ground. Yet many of them are detected at Earth's surface. The reason is time dilation. These muons are moving at speeds close to the speed of light. From Earth's frame of reference, their internal clocks tick more slowly. Their short lifetimes stretch out just enough for them to survive the journey downward. The number of muons detected matches the predictions of special relativity precisely. Atomic clocks provide another striking confirmation. When highly accurate clocks are flown on aircraft or placed aboard satellites, they accumulate time at different rates compared to clocks left on the ground. The differences are small but measurable. When the clocks are brought back together, the discrepancies are exactly what special relativity predicts once motion is taken into account. These experiments demonstrate that time dilation is not an illusion, or a matter of perspective. It is a physical effect that alters the rate at which time passes for moving systems. Closely related to time dilation is the relativity of simultaneity. In everyday life, simultaneity seems obvious. Two events either happen at the same time or they do not. This judgment feels objective and absolute. In special relativity, it is not. Whether two distant events are simultaneous depends on the observer's state of motion. This arises directly from the way clocks are synchronized. To decide whether two spatially separated events occur at the same time, one must define a procedure. Special relativity uses light signals for this purpose, because the speed of light is the same for all observers. An observer sends a light signal to two distant clocks and adjusts them so that the signals return symmetrically. This defines simultaneity for that observer. But another observer moving relative to the first will not agree that the signals were exchanged symmetrically. As a result, they will not agree on which events happened at the same time. This disagreement is not caused by signal delays or imperfect instruments. It is built into the structure of space-time itself. Hermann Minkowski provided a powerful way to understand this by unifying space and time into a single geometric framework. In Minkowski's formulation, events are points in space-time rather than locations evolving in time. Different observers correspond to different ways of slicing space-time into space and time. Each observer's notion of what counts as space at a given moment depends on their motion. In this picture, simultaneity becomes a choice of slice through space-time. One observer's slice intersects events in one pattern. Another observer's slice, tilted differently because of relative motion, intersects a different pattern of events. Both descriptions are valid. Neither has priority. This geometric view removes much of the apparent paradox. Instead of asking which events are truly simultaneous, special relativity asks which events are simultaneous for a given observer. The laws governing these relationships are precise and consistent. What disappears is the idea of a universal present moment shared by everyone. There is no single global now. Each observer carries their own present, defined by their motion through space-time. These presents overlap locally but diverge at distance. Two observers standing next to each other agree on what is happening here and now, but if they move relative to one another, their definitions of distant simultaneity drift apart. This is deeply counterintuitive, but it is unavoidable. If a universal now existed, it would define a preferred state of rest. That would contradict the principle that the laws of physics are the same for all observers in uniform motion. The absence of a universal now is not a philosophical inconvenience, it is a physical necessity. Despite its strangeness, this framework has been tested exhaustively. Particle accelerators routinely produce particles moving at speeds close to the speed of light. Their lifetimes, decay patterns, and interactions match relativistic predictions with extraordinary accuracy. Global navigation systems depend on precise timing corrections that include special relativistic effects. Without these corrections, positioning errors would grow rapidly. Even everyday technologies quietly rely on these principles. Modern communication networks synchronize signals across vast distances. The timing protocols assume the relativistic structure of time. Engineers may not think about space-time geometry while designing these systems, but the systems work because the underlying physics is correct. Special relativity has survived every experimental challenge thrown at it. The combination of time dilation and the relativity of simultaneity leads to a profound conclusion. Time is not a single shared dimension flowing identically for all observers. It is part of a larger structure in which measurements depend on motion. This does not mean time is arbitrary or subjective. The rules are strict. Transformations between observers are exact. Given the motion of one observer relative to another, the relationship between their measurements of time is fixed. What disappears is not order, but universality. There is still cause and effect. There is still a clear distinction between past and future for every observer. Signals cannot travel faster than light, ensuring a consistent causal structure. What changes is how different observers carve that structure into moments. This distinction is subtle but crucial. Special relativity does not say that anything can happen in any order. It says that events which cannot influence one another may be ordered differently by different observers. The structure of causality remains intact. The calm elegance of this framework is easy to miss. Instead of forcing the universe to obey human intuition about time, special relativity allows time to behave as it must, in order for the laws of physics to be consistent. The result is not chaos, but a deeper kind of order. Once time is understood in this way, space can no longer be treated as a passive container either. Distances depend on motion just as durations do. Space and time become aspects of a single entity, each shaping how the other is measured. This unified picture works beautifully as long as gravity can be ignored. Special relativity describes how time behaves for observers in uniform motion, far from massive objects and strong gravitational fields. Within that domain, it is complete and self-consistent. It tells us how clocks behave, how events are ordered, and why no universal present exists. But nature does not always cooperate by remaining free of gravity. Mass bends trajectories. Energy alters motion. Clocks placed in different gravitational environments tick at different rates, even when at rest relative to one another. These effects lie beyond the scope of special relativity. To understand them, the structure of space-time itself must become dynamic, and that requires taking the next step. Once space and time are understood as inseparable, the idea of a universal clock quietly dissolves. In the relativistic view, events do not happen inside time as if time were a container. Instead, events are points within space-time itself. Each event has both spatial and temporal relationships to other events, and those relationships depend on how an observer moves through the universe. This shift sounds abstract, but it carries very practical consequences. In space-time, there is no single privileged way to divide the universe into moments. There is no universal slicing that everyone must agree on. What feels like a natural separation between space and time turns out to be a choice, not a fact. To see why, it helps to think geometrically. Space-time can be imagined as a four-dimensional structure where each event is fixed, but the way it is described depends on perspective. An observer moving through space-time traces out a path called a world line. Along that path, the observer's clock measures proper time, the time experienced by that observer alone. Now consider how an observer defines what is happening at a particular moment. They choose a slice through space-time, a three-dimensional surface that represents all of space at what they consider to be the same time. This process of slicing space-time into spatial snapshots is known as foliation. Different observers choose different foliations. An observer at rest relative to Earth might slice space-time one way. An observer moving at high speed relative to Earth will slice it differently. Both choices are valid. Neither is more real than the other. There is no unique way to carve space-time into universal moments. This lack of uniqueness is not a flaw, it is a feature. Special relativity already hinted at this through the relativity of simultaneity. Space-time geometry makes it explicit. Simultaneity is not built into the universe. It emerges from how an observer chooses to define time. Once this idea is accepted, the notion of a global clock begins to lose meaning. A global clock would require a preferred foliation, a single slicing of space-time that defines a universal present everywhere. But relativity allows no such preference. The laws of physics do not select one slicing over another. Every choice of time coordinate is equally valid. This becomes even clearer when physicists attempt to describe space-time in ways that resemble the familiar structure of evolving systems. In the mid-20th century, Richard Arnowit, Stanley Deezer, and Charles Misner developed what is now known as the ADM formalism. Their work was not motivated by philosophy. It was motivated by the practical challenge of describing gravity in a way that could be analyzed, computed, and eventually quantized. The ADM formalism rewrites spacetime in terms of evolving spatial geometries. It treats spacetime as a sequence of three-dimensional spaces that change over time. This looks reassuringly familiar, almost like classical physics where systems evolve step by step. But there is a crucial difference. In the ADM approach, the choice of how to slice spacetime into these spatial layers is not fixed by the theory. Physicists are free to choose different foliations depending on convenience. The equations adjust accordingly. The physical content remains the same. This freedom is known as coordinate freedom or gauge freedom. It means that the time parameter used in calculations is not unique. It is a label chosen to make the mathematics manageable, not a reflection of a universal ticking clock. In practical terms, this means that time becomes a bookkeeping device. Physicists choose a time coordinate to track how things change, but the coordinate does not correspond to anything physically privileged. Different choices of time coordinate describe the same underlying spacetime, just from different perspectives. This idea can feel unsettling at first. In everyday experience, time feels fundamental. It feels like the thing against which everything else happens. In relativistic physics, that role is taken over by space-time geometry. Time is one way of parameterizing that geometry, not an independent entity flowing on its own. The absence of a preferred global time has important consequences. It means there is no universal definition of simultaneity. It means there is no single answer to the question of what is happening everywhere right now. It means that time, as used in equations, must always be understood as local and observer-dependent. This does not make physics vague or arbitrary. On the contrary, it makes it more precise. All observers agree on space-time intervals, on causal relationships, and on the structure of physical laws. What they do not agree on is how to divide that structure into moments. To appreciate how deeply this runs, consider that even in flat space-time, without gravity, there are infinitely many valid ways to define time. Each corresponds to a different family of observers, each moving differently through space-time. None of these observers is more correct than the others. Once gravity is included, this freedom becomes even more significant. Gravity is not a force acting within spacetime. It is the curvature of spacetime itself. Mass and energy determine how spacetime bends, and that bending determines how objects move and how clocks tick. In curved spacetime, the idea of a global clock becomes even harder to sustain. Spacetime may not admit any foliation that covers the entire universe in a simple way. In some geometries, no single slicing can extend everywhere without running into singularities or breakdowns. Even when a global slicing exists, it is never unique. This reinforces the idea that time coordinates are tools, not truths. Physicists choose them to solve problems, to model systems, and to make predictions. But the universe does not carry a label saying which choice is correct. This perspective resolves a subtle confusion. When relativity says that time is relative, it does not mean that time is subjective or ill-defined. It means that the universe does not provide a single global temporal structure that everyone must share. Time is woven into space-time, and space-time responds to matter and energy. What remains universal is not time itself, but the rules that govern how time behaves. All observers agree on how to translate between different descriptions. All observers agree on which events can influence which others. Causality remains intact. What disappears is the idea of an absolute temporal background. This realization prepares the ground for the next step. If time is part of space-time, and if space-time itself can bend and curve, then time cannot remain uniform in the presence of gravity. Clocks placed in different gravitational environments will not tick at the same rate, even if they are not moving relative to one another. This is not a small correction, it is a fundamental consequence. The geometry of space-time determines how time flows. Once geometry becomes dynamic, time becomes dynamic as well. The quiet end of the universal clock is not a dramatic collapse. It is a natural consequence of taking space-time seriously as a physical object. Time does not vanish, it becomes local, and that local nature of time is about to become unavoidable. When gravity enters the picture, time stops being merely relative and becomes deeply physical. In general relativity, gravity is not treated as a force pulling objects through space. It is treated as the geometry of space-time itself. Mass and energy tell space-time how to curve, and that curvature tells objects how to move. Clocks, like everything else, follow paths through this curved structure. This shift changes the role of time fundamentally. In Newtonian physics, gravity acts within space and time. In general relativity, gravity reshapes space and time. Time is no longer a background parameter that remains untouched. It becomes something that responds directly to the distribution of matter and energy. This idea can sound abstract, but its consequences are precise and measurable. Einstein's field equations describe how space-time curvature depends on mass and energy. Solving these equations is difficult in general, but early in the development of the theory, Karl Schwarzschild found an exact solution for a simple but important case. He described the space-time geometry outside a spherical, non-rotating mass. This solution revealed something remarkable. Near a massive object, time does not flow at the same rate as it does far away. A clock closer to the mass ticks more slowly than a clock farther from it. This effect is not caused by motion. It arises purely from the curvature of space-time. This phenomenon is known as gravitational time dilation. Closely related is gravitational redshift. Light climbing out of a gravitational field loses energy. Its frequency decreases, shifting toward the red end of the spectrum. This shift can be understood as a consequence of time itself running at different rates. Light emitted where time passes more slowly arrives in a region where time passes more quickly, and its oscillations are stretched. Gravitational redshift was first confirmed experimentally in the mid-20th century using precise measurements of gamma rays traveling upward in Earth's gravitational field. The results matched Einstein's predictions exactly. These effects are not confined to exotic environments. On Earth, gravitational time dilation is small but real. A clock at sea level ticks slightly more slowly than a clock on a mountain. The difference is tiny, amounting to fractions of a second over many years, but it can be measured with modern atomic clocks. This matters because clocks are physical objects. A clock is not an abstract marker of time. It is a system undergoing regular physical processes. In general relativity, those processes are affected by space-time curvature. A clock placed in a stronger gravitational field experiences less proper time than one placed in a weaker field. There is no escaping this. No engineering trick can shield a clock from gravity. The rate at which it ticks is determined by the geometry of space-time along its path. This realization marks a profound departure from earlier ideas. Time is no longer something that exists independently of matter. It is shaped by matter. The presence of mass changes how time flows. Two identical clocks, built side by side and synchronized carefully, will drift apart in their readings if placed in different gravitational environments. This is not a failure of synchronization. It is the expected behavior of time itself. One of the most practical demonstrations of this comes from satellite navigation systems. Satellites orbiting Earth carry highly precise atomic clocks. These clocks experience weaker gravity than clocks on the ground because they are farther from Earth's mass. As a result, they tick faster. At the same time, the satellites are moving at high speeds relative to Earth's surface, which causes time dilation from motion, making their clocks tick more slowly. Both effects occur simultaneously. The gravitational effect is larger than the effect from motion. If left uncorrected, the clocks on satellites would gain several microseconds per day relative to clocks on Earth. That may sound insignificant, but in navigation systems, timing errors translate directly into position errors. A discrepancy of even a few billionths of a second would quickly lead to errors of many meters. To prevent this, satellite clocks are pre-adjusted and continuously corrected using predictions from general relativity and special relativity. The system works precisely because time behaves exactly as Einstein described. This is not a theoretical test performed under rare conditions. It is a daily confirmation embedded in ordinary technology. Every time a navigation system provides an accurate position, it quietly affirms that gravity affects time. General relativity does not merely predict that time varies with gravity, it explains why. Space-time curvature changes the paths available to clocks. A clock measures the length of its path through space-time, known as proper time. In curved space-time, different paths accumulate different amounts of proper time, even if they begin and end at the same events. This means that time itself is path-dependent. Two clocks can start together, separate and reunite, and show different elapsed times. The difference is not an illusion. It reflects the geometry they traversed. This idea extends naturally to stronger gravitational fields. Near extremely massive objects such as neutron stars or black holes, gravitational time dilation becomes dramatic. A clock hovering close to such an object ticks much more slowly compared to a clock far away. From a distant perspective, processes near the massive object appear to slow down. This does not mean time stops in any absolute sense. For the clock near the mass, time proceeds normally. What changes is the relationship between different regions of space-time. There is no single rate at which time flows everywhere. In general relativity, the concept of a universal clock is not just absent, it is incompatible with the structure of the theory. Each clock carries its own time, shaped by the space-time it inhabits. This is a natural extension of the ideas already present in special relativity. Motion affects time. Gravity affects time. Both are expressions of space-time geometry. What general relativity adds is the realization that geometry itself is dynamic. Space-time is not fixed. It responds to mass and energy. As a result, time cannot remain fixed either. It bends, stretches, and varies in response to physical conditions. This realization resolves old inconsistencies but introduces new challenges. General relativity provides a complete description of how time behaves in gravitational fields. It predicts gravitational redshift, time dilation, and the influence of curvature with extraordinary accuracy. These predictions have been confirmed repeatedly. At the same time, this picture deepens the tension with quantum mechanics. Quantum mechanics relies on a single shared time parameter. General relativity denies that such a parameter exists globally. In regions where gravity is strong or space-time is highly curved, there is no obvious way to define a universal time that all systems can use. This is not a technical inconvenience. It is a conceptual divide. Time in general relativity is local, physical, and dynamical. It is tied to space-time geometry. It is influenced by mass and energy. It is not an external backdrop. As gravity grows stronger, these features become impossible to ignore. The quiet corrections applied to satellite clocks hint at what happens when gravity's influence on time becomes dominant. Near extreme objects, the differences grow large. Time flows at dramatically different rates in different regions. Understanding this regime requires taking space-time seriously as a physical entity. And once space-time becomes extreme, the comfortable assumptions inherited from earlier theories begin to strain. The universe has more to say about time, and it speaks most clearly where gravity is strongest. As gravity grows stronger, time begins to behave in ways that no longer feel subtle. The gentle differences measured by atomic clocks on Earth give way to dramatic distortions. The steady assumptions that worked so well in laboratories begin to strain. In regions where matter is crushed to extreme densities, time itself becomes stretched, slowed, and deeply uneven across space. Neutron stars provide one of the clearest examples. These objects are formed when a massive star exhausts its fuel and collapses under its own gravity. What remains is a sphere only a few tens of kilometers across, yet containing more mass than the Sun. The density is extraordinary. A single teaspoon of neutron star material would outweigh a mountain. In such an environment, space-time curvature is intense. A clock placed on the surface of a neutron star would tick significantly more slowly than a clock far away. The difference is no longer a tiny correction measured over years. It is large enough that seconds and minutes begin to diverge in noticeable ways. From a distant perspective, processes near the surface appear slowed, as if time itself is thickened by gravity. This is not hypothetical. Astronomers observe neutron stars through their radiation, often emitted as regular pulses when the star rotates. These pulses arrive with astonishing regularity, allowing precise measurements. When the gravitational environment is taken into account, the timing matches the predictions of general relativity. The star's intense gravity alters how time flows, and the signals reflect this. If neutron stars stretch time, black holes push it to its limits. A black hole forms when gravity overwhelms all known forces, compressing matter into a region from which nothing, not even light, can escape. Surrounding this region is the event horizon, a boundary beyond which the structure of space-time becomes profoundly altered. Near the event horizon, time dilation becomes extreme. For an observer far away, a clock falling toward a black hole appears to slow dramatically. As it approaches the horizon, its ticking seems to stretch out indefinitely. Signals become redshifted, growing weaker and longer in wavelength as the clock's time slows relative to the distant observer. From the clock's own perspective, however, time does not stop. The clock ticks normally as it falls. This contrast highlights a crucial point. Time in general relativity is always local. Each observer carries their own measure of time, shaped by their path through space-time. There is no single answer to how fast time is passing near a black hole. The answer depends on where you are and how you are moving. This behavior is not speculative. It follows directly from the equations of general relativity, and those equations have been tested wherever testing is possible. But there are limits to what can be observed. No signal can emerge from inside the event horizon. The internal structure of black holes is hidden from direct measurement. What happens at the very center, where curvature becomes extreme, lies beyond observational reach. This is where the work of Roger Penrose becomes especially important. Penrose studied the mathematical structure of space-time under extreme conditions. He showed that, under very general assumptions, gravitational collapse leads inevitably to singularities. These are regions where space-time curvature becomes infinite, and the known laws of physics break down. Penrose's singularity theorems do not describe what happens at a singularity. They demonstrate that general relativity, taken seriously, predicts its own limits. In these regions, concepts like distance and duration lose their usual meaning. Time, as measured by clocks and trajectories, cannot be extended smoothly through a singularity. The theory itself stops providing answers. This is not a failure of imagination. It is a signal that a deeper description is required. Importantly, Penrose emphasized restraint. The existence of singularities does not mean that physics becomes meaningless everywhere near them. It means that the classical description of space-time reaches a boundary. Predictions remain reliable up to that boundary. Beyond it, the theory does not apply. This distinction matters. Popular accounts often drift into speculation when discussing black holes, imagining time freezing or reversing in dramatic ways. General relativity does not require such narratives. It provides precise predictions about how time behaves outside and near extreme objects, and it remains silent where its assumptions fail. That silence is not ignorance, it is honesty. Observational evidence supports this careful approach. Astronomers infer the presence of black holes through their gravitational influence on nearby matter, the motion of stars, and the emission of radiation from hot materials spiraling inward. Timing measurements of these signals reveal effects consistent with extreme gravitational time dilation. Gravitational waves, detected from merging black holes, also carry timing information. The waves arrive with patterns that encode how space-time itself oscillates during violent events. These observations confirm the predictions of general relativity in regimes far more extreme than any laboratory experiment. Yet even here, there are boundaries. The internal behavior of time near singularities remains unknown. No experiment can probe it directly. The equations point toward infinities, which usually signal that a theory has been pushed beyond its domain. This is where speculation must be resisted. General relativity predicts that time behaves in extreme ways near black holes, but it does not tell us what happens when space-time curvature becomes infinite. Any claim beyond that requires a theory that goes beyond general relativity itself. Neutron stars and black holes therefore occupy a special place in the story of time. They are environments where the assumptions of earlier theories fail. They force time to reveal its dependence on gravity. They expose the limits of classical descriptions, and they do so without ambiguity. At the same time, they highlight a growing tension. General relativity treats time as local, dynamical, and shaped by geometry. Quantum mechanics treats time as global, fixed, and external. In the environments just described, both frameworks would seem to be required. Matter behaves quantum mechanically. Gravity is intense. Time is distorted. Yet there is no single theory that comfortably describes all of this at once. Near neutron stars, quantum effects influence the behavior of matter, while gravity influences the structure of space-time. Near black holes, both become unavoidable. The deeper one looks, the clearer the mismatch becomes. This mismatch is not merely technical. It concerns the role of time itself. In extreme gravity, time cannot be treated as universal background. It varies from place to place, it responds to energy, it becomes part of the physical system. Quantum mechanics, as it stands, is not equipped to handle this. The theory assumes a single time parameter that orders events everywhere. Near black holes, no such parameter exists. There is no natural way to synchronize clocks across regions of strong curvature. There is no preferred slicing of space-time to serve as a universal timeline. This does not mean quantum mechanics fails in everyday circumstances. It means that its assumptions become questionable in extreme regimes. Neutron stars and black holes therefore act as signposts. They mark the edges of our understanding. They show where successful theories meet their limits. They reveal that time, when pushed hard enough, refuses to fit neatly into any single framework. The stretching of time under extreme gravity is not a curiosity. It is a clue. It suggests that time is not a simple ingredient added to the universe at the beginning. It is something that emerges from deeper structures that change under extreme conditions. Understanding those structures requires care, restraint, and a willingness to accept uncertainty where evidence runs out. The universe does not offer answers lightly. It reveals them gradually, often by showing where old ideas can no longer hold. And in the regions where gravity stretches time to its limits, those cracks become impossible to ignore. At this point, two remarkably successful descriptions of the universe stand side by side. Both are precise. Both are experimentally confirmed. Both explain vast ranges of physical phenomena with extraordinary accuracy. And yet, when it comes to time, they speak different languages. In quantum mechanics, time is absolute. It exists outside the system being studied. It flows uniformly. It is the same everywhere. Every quantum process evolves with respect to a single shared time parameter that never fluctuates, never bends, and never responds to what the system is doing. Time orders change, but it is not changed by it. In general relativity, time is relative. It is woven into space-time. It depends on motion and gravity. It flows at different rates in different places. It cannot be separated cleanly from space, and it certainly cannot be assumed to tick identically everywhere. Each observer carries their own measure of time, shaped by the geometry of space-time along their path. These are not minor differences in interpretation. They are fundamentally different roles assigned to time itself. Quantum mechanics treats time as a fixed background. General relativity treats time as a dynamic participant. One assumes a universal clock. The other denies that such a clock can exist. This difference is often described casually as a disagreement, but that word can be misleading. It suggests that one theory must be wrong and the other right. That is not the situation. Both theories work. Quantum mechanics predicts atomic behavior, chemical bonding, electronic devices and quantum technologies with stunning precision. General relativity predicts gravitational time dilation, black hole dynamics, gravitational waves, and the large-scale structure of the universe with equal success. The tension arises not from failure, but from success. Each theory is internally consistent. Each is confirmed within its domain. The problem appears only when one attempts to apply both at the same time. To understand why, it helps to introduce two concepts that quietly govern how physical theories are built: background dependence and background independence. A background-dependent theory assumes a fixed stage on which physical processes unfold. That stage does not react. It does not evolve. It simply exists. Classical mechanics and standard quantum mechanics both rely on such a background. Space and time are given in advance, and physical systems move and change within them. A background-independent theory, by contrast, does not assume any fixed stage. The geometry itself is part of the system. It evolves. It responds. It cannot be specified independently of the matter and energy it contains. General relativity is the prime example of this approach. In general relativity, space-time is not a backdrop. It is a physical entity governed by equations. There is no fixed geometry waiting in advance. The structure of space and time emerges dynamically from the distribution of mass and energy. This difference is crucial. Quantum mechanics assumes a fixed time parameter precisely because it is background dependent. It needs a stable reference to define evolution, probabilities, and measurement outcomes. Without that reference, the standard formulation does not function. General relativity rejects such a reference. It does so not out of preference, but because experiments demand it. Gravity affects clocks. Motion affects time. A fixed background would contradict observed reality. This is where John Wheeler's framing becomes especially helpful. Wheeler emphasized that the difficulty is not that the theories contradict one another in their predictions. It is that they are built on incompatible conceptual foundations. One requires a background, the other removes it. Wheeler famously summarized the challenge with the simple idea: quantum mechanics needs space-time to exist before it can describe anything. General relativity says space-time itself is something to be described. Both cannot be simultaneously true in the same way. This is what is meant by a structural mismatch. Quantum mechanics asks how systems evolve in time. General relativity asks how time itself behaves. One takes time as an input. The other produces time as an output. Trying to merge them without addressing this difference is like trying to write a story in which the page both exists in advance and is created by the words as they are written. Each description works on its own terms. Together they clash. It is important to be precise here. Quantum mechanics does not deny that time can behave differently in different circumstances. It simply does not include those effects